So in this lecture, I'll add some more comments of what we have studied in the last class. Agreed? So first we have Maxwell equation. Second, from the Maxwell equation, we derive that electromagnetic field can be a wave. Okay, so because the electromagnetic field was satisfying a wave equation, and this wave equation we got from the Maxwell equations itself. So this is the wave equation that we got from Maxwell equations itself. This wave equation is really big one because your Laplacian is del x square, del y square, and del z square. Agreed? But the story doesn't end here. If your electric field has three components, then this equation can have about, so if the electric field has three components, then this equation can have a total of 9 terms for the left hand side, and these 9 terms are written here below. Agreed? You can see it, all the 9 terms are written here. Now we have this big equation only when the electric field has all the three components, that is Ex, Ey, and Ez. Now we can simplify this equation. Consider if I make my Ez 0. So let us try to understand what is the meaning of this. Okay, so let us try to understand in 2D first. Okay, consider your electric field, okay, is written as EXI. So what is the meaning of electric field written in the in the x axis? It means that this electric field that you have taken, it means that the electric field that you have taken has vibrations only along the x axis. So if I can draw a diagram, so you see it has vibration only along x direction. The vibrations are here, so I'm giving arrows. These represent the vibration. What if you write your electric field in y? So consider your electric field is EYJ. So when you say your electric field is in y direction, you are assuming that any vibration in the x and the z direction is not occurring. Then the diagram will look like this. So this is when your electric field is vibrating only along y direction. Now you see, in both these cases, what I have done is that my wave is traveling along z direction. In the first case, my wave is traveling along z direction. Even in the second case, my wave is traveling along the z direction. So if the wave is traveling along z direction, then automatically in the first case there is no vibration of electric field in the z direction, so it is 0. Even in the second case, Ez is automatic 0. So in the direction of motion, in the direction of propagation, there can never be any electric vector oscillating. Agreed? Now in the first case, even not only Ez is 0, Ez is 0 because the wave is traveling along the y axis, in the z axis. So in the first case, I have also assumed my Ey to be 0. So you see there is no vibration along the y axis. So these vibrations, they don't exist. In the second case, Ez is, in the second case here, Ez is 0 because the wave is traveling along the z axis, and you see Ex is also 0. Ex is also 0. Now what if I do the following? What if I have an electric field which can be written both in the x and the y? So what is this electric field and what will be the diagram of this electric field? So it has a component in the x direction and it has a component even in the y direction. So how to represent this type of fields now? So let me draw the diagram of this field. So it looks like this. So I know the diagram is not clear, but let me give you a hint that the electric field is vibrating like this. How to make this clear? So let me give you one hint. This electric field, which is Ex and Ey, okay, so the electric field is neither vibrating in the x direction nor it is vibrating in the y direction. It is vibrating somewhere in between x and y. Okay, so let us look from this direction. So if we look at from this direction, then what we will see? Then we will see that there is an x-axis and there is an y-axis. Okay, and the z-axis is say it goes inside the screen. So z-axis is inside the screen. So this is your x and that is your y. So in the case 1, so say this is case 1. In the case 1, the electric field was vibrating along the x-axis alone. In the case 2, the electric field was vibrating along the y-axis alone. In the case 3, so this is the case 3 where it can have both the vibration, it can have a component in x and y, then the electric field is actually vibrating along this direction. And since the electric field is vibrating along this direction, I can draw that, I can say that this electric field has an x component, and I can also say that this electric field has a y component. So this is the meaning of when the electric field is vibrating along vibrating such that it has an ex vibration and it has an ey vibration. So these are complicated things. So to make our life simple, what we did not assume an electric field of this form. So we did not assume an electric field of this form. So let me drop this part. We assumed an electric field of this form, the first one. Why we took the first one? Because this will simplify the entire big equation. So this big equation with 9 terms, this will get simplified. So let us see how this will get simplified. Okay, remember that the denominator represents the direction in which the propagation is happening. So I have an electric field that is vibrating along x-axis, and this electric field is propagating along the z-axis. So is this term is not going to remain, because though my electric field is vibrating along x-axis, but the direction of propagation is z, not x. So this term will not remain. So this term is not going to remain because I don't have any electric field in y-axis. I don't have any electric field vibration in z-axis. I have an electric field vibration in x-axis, but I don't have the propagation in z-axis. So this is not going to remain. This gets cancelled. And this 2 gets cancelled, and I'm left with this. See, I have a vibration of electric field along x-axis and I have a propagation along z-axis. So my choice of having an electric field vibrating only along x-axis makes this big equation very small. So all the term that gets cancelled. So let me just delete it. Okay, these all terms gets cancelled, and we are left with this simple equation here. So this was our purpose, to make the equation simple, to make our life simple. So this was our purpose. So we have only one term remaining. So let me write it down. So we have only one term remaining. Let me put it here. Yep. So the choice, so my choice of having an electric field which is oscillating along x-axis and the electric field is propagating along the z-axis leaves me with a simplified wave equation, very simplified wave equation. Then what we did, then we took the solution. So what was the solution of Ex we took? The vibration of Ex is fundamentally oscillating vibration, so it's a form of wave, because you see Ex satisfies a wave equation. So I took, in the last lecture, I took this as E naught x, okay, and I assumed a cos solution. So this is an equation of a wave. So cos omega t minus kx. So this was what we did last time. Then what we did to make life, but our main purpose was calculating the magnetic field the if I take an electric field Ex, then question is what will be the corresponding magnetic field. That was found out by using this formula, that is curl of B. So as we have done in last lecture, what do we find? We found that the magnetic field was actually vibrating along the y-axis. Okay, so magnetic field was actually vibrating along the y-axis, and the phase of the magnetic field is same as the phase of the electric field. Not only the phase is same, I mean both have the cos term, but also the velocity is same. In both case we have the same omega and we have the same k. So velocity of this velocity of propagation of electric and magnetic field, they are same, that is the speed of light, and they are at 90°. Agreed? So this is the summary of what we did in our last class. Now so the reason we did the summary here is I want to emphasize on the fact that the wave equation that we get from the Maxwell equation is not that easy. It is filled with bigger and bigger terms. As I said, this part has 9 terms. So if I would have taken a wave equation E, which could have been written as say Ex and Ey. So if it would have contained two components, Ex and Ey, then the solution would have been a bit tough. Why the solution would have been tough? So keep it as an exercise and take it as an exercise, and can you guess how many terms would have been in our wave equation if I would have taken Es, Ex and Ey? So take it as an exercise. So now that we have understood that we have this electric field and magnetic field which are 90° to each other and they form an electromagnetic wave. Now we know that there is something called as electromagnetic wave. So let us calculate, let me draw an electromagnetic wave. So this diagram presents you with an electromagnetic wave, and you can see how the waves are perpendicular to each other. So if you can take a close look, we have a wave along this direction vibrating, and we have a vibration along this direction. So this is the vibration of electric field and this is the vibration of magnetic field. Agreed? And say it is traveling along the z axis. Similarly, you can have these are the different forms of electromagnetic wave. Here the magnetic field is vibrating along the positive y direction. In second diagram, the magnetic field is vibrating along the starting has a vibration along the negative y direction. Agreed? So it depends where you take your axis. Now my main aim here is to calculate the energy in an electromagnetic wave. So let us see. So you know that an electromagnetic wave has the electric field and it has the magnetic field. So it contains both the field. And we also have calculated in our previous CD the energy stored in each of the field. So can you tell me what is the energy density that is stored in the electric field of the EM wave? The energy density in the electric field of the EM wave can be given as half epsilon naught E square. What is the energy density for the magnetic field? We know that energy density stored in a magnetic field is B square by 2 mu naught. But we can simplify this. How? Remember that we saw in an electromagnetic wave that B was actually 1 by C times the electric field. So what was the C? C was nothing but mu naught epsilon naught. Mu naught into epsilon naught. Agreed? So you can write, so C was 1 by, so it's 1 by. So you can write this term, this energy term as half epsilon naught E square. Okay, this is the energy density. And for the magnetic field, what I can do is, let me replace it. So I'll get an E square here, and then I will get a mu naught square and an epsilon naught square here, and then I'll have a 2 mu naught here. Oh, c was 1 by root over of this, so I don't have any square, so made a mistake, so won't have any square here. Agreed. Now, so what happens, the mu naught, they get cancelled. So the after cancelling the mu naught, you are left with half epsilon naught E naught square here and half epsilon naught E naught square here. So what is the total energy stored in an electromagnetic field? The energy density, that is the energy stored per unit volume of the electromagnetic field, is half epsilon naught E naught square. So this is the total energy density for an electromagnetic wave. So what information does this thing carry? First of all, it says that if you have the idea of the electric field, if you have the idea of the average electric field of this electromagnetic wave, then even without the idea of magnetic field, you can calculate the total energy of this EM wave. Agreed. This also says a very interesting thing. The interesting thing says that these two are same. How these two are same? Because when we use this particular thing, this particular formula in our equation, we found that the first equation is half epsilon naught square and second equation is also half epsilon naught square. So what is so special that we found that the first term is equal to the second term? The special thing about this is that the electric field and magnetic field both they like exchange energy and keep each other alive. Agreed. So one in the other, I can say one in the other. So how does an electromagnetic wave move? So how does it sustain itself without a material medium? It sustains itself without a material medium because the changing electric field produces a changing magnetic field here, and in turn this magnetic field creates this electric field. So they are like moving hand in hand. So one creates the other creates the other, and in this way, without the use of material medium, the electric field and magnetic field, they can exist even in vacuum because they create each other. And who said that they are creating each other? Maxwell equation. Remember, Maxwell equation says that a changing electric field can create a magnetic field, and a changing magnetic field can create an electric field. So this is how the electromagnetic wave is traveling forward. Now we'll discuss more in the next lecture. Okay, so we end our lecture here. We'll discuss more in the next lecture.